All right, let's talk about something that gets everybody when they're starting out with Verilog. Seriously, it's one of those hidden traps that can cause the most frustrating bugs imaginable. But don't worry, today we're going to figure it all out. So it all boils down to these two little guys. On the left, you've got your standard equal sign, and on the right, you've got this one with the little arrow. They look so similar, right? But in the world of hardware, that tiny little difference, well, it's a world of difference. It means you're building two totally separate kinds of circuits. And I'm not kidding here. One of these will build you a beautiful, perfect circuit that does exactly what you want. The other one? It's going to give you nothing but chaos. Race conditions, simulations that lie to you, a total mess. So, are you ready to find out which is which? Okay, so to really wrap our heads around this, we need to take a quick step back. Before we can even talk about these operators, we have to talk about the two fundamental worlds of hardware they help create. It really all comes down to how a circuit thinks about time and memory. First up, we have what's called combinational logic. The idea here is simple. What you get out depends only on what you put in right now. There's zero memory of the past. Think about a basic calculator. You punch in 2 plus 2 and you get 4, instantly. It doesn't care that you calculated 5 plus 5 a second ago. It's totally stateless. And then you have sequential logic. And this is where things get really cool. With these circuits, the output depends on what's coming in now and what the circuit's state was a moment ago. They have memory, usually little things called flip-flops. And everything is synchronized by this master metronome, the clock signal. Every single tick of that clock is a chance for the circuit to move to its next state. Okay, now that we have that background, we can finally go back and look at our two main suspects, the blocking and non-blocking assignments. You can think of these as the two different languages we use to describe those two different hardware worlds we just talked about. So first, let's talk about the blocking assignment, the plain old equal sign. And honestly, its name says it all. When the simulator hits a line of code with this operator, it executes that line and it blocks everything else from happening until it's done. It's immediate. One thing happens, then the next, A to B to C. The easiest way to think about this is like a to-do list, right? You can't drink your coffee until you've finished making it. Task 1 has to be done before you can even think about starting task 2. That first task blocks the second one. That's a blocking assignment in a nutshell. Now let's get to the non-blocking assignment, the less than operator. This guy works in a completely different way. It's kind of a two-step process. In a block of code, the simulator first sweeps through and looks at all the non-blocking lines. It calculates the results for everything on the right-hand side based on the values that existed at the start of that moment. Only after it's figured all that out, then it assigns all those results to the variables on the left, all at the same time. The perfect analogy here is a flash mob. You know, everyone gets the plan ahead of time, they know what they're supposed to do, they all look at the situation at the start, then, on some signal, like our clock tick, everybody does their move at the exact same time. Nobody is waiting for anybody else to finish first. That is the whole idea behind non-blocking. It's parallel, it's coordinated. All right, so analogies are great and all, but the real proof is in the pudding, right? Let's see how this actually plays out in code. We'll take a super simple 2-line example and watch how these two operators create completely different results. Okay, check this out. We're using blocking assignments here. So when the clock ticks, that first line, Q1 equals D, happens immediately. Boom, D's value is now in Q1. Because it's blocking, the simulator then moves to the second line. And when it executes Q2 equals Q1, what value does it see for Q1? It sees the new value it just got. So in a single clock cycle, the value from D flows all the way through to Q2. What we've described here is basically just a wire. Now let's just swap in the non-blocking assignments. Same code, different operator. At the clock edge, remember the two-step process? The simulator first looks at the right-hand side of both lines. It grabs the value of D, and it grabs the original value of Q1, the value it had before anything changed. Then it does the assignments. Q1 gets the new value from D, and Q2 gets that old value of Q1. What did we just make? A two-stage shift register, 2 flip-flops, a totally different circuit. See the difference? So we've seen the theory. We've seen a tiny example. Now let's put it to the test with a real circuit, where choosing the wrong operator doesn't just make a different circuit, it leads to a catastrophic failure. Welcome to the case of the broken ring counter. So our goal here is pretty simple. We want to build a 4-bit ring counter. All that means is we want to take a register, put a single 1 in it, And then on every clock tick, just shift that 1 over one spot and have it wrap around from the end back to the beginning. It's a super common fundamental building block you see everywhere. So someone new to Verilog might look at this problem and write this code using blocking assignments. I mean, the logic seems to make sense, right? Step 1, shift everything to the left. Step 2, take the bit that fell off the end and stick it back on at the beginning. Seems reasonable. But let's see what actually happens when we simulate this. And here's the disaster. We start with our 1,000. The first blocking statement executes immediately. Count equals count shifted 1. That 1 that was in the third position gets shifted out, and it's gone. Poof. The register is now all zeros. Only then does the second line get to run. It tries to copy count 3, but count 3 is now a 0. So the final result is 0, 0, 0, 0. The 1 is just lost. It's a complete failure. The blocking assignment literally destroyed the data we needed for the next step. Our 1 is gone forever, and our so-called counter is now just stuck at 0. This is a classic bug. Okay, let's hit the rewind button and try this again. This time we'll use the right tool for the job, non-blocking assignments. The code looks almost exactly the same, right? We just changed the equal sign to a slasher equal sign. But the result? Well, it's night and day. And here we go, this is how it's done. At the clock edge, our count is 1,000. The simulator looks at both right-hand sides before doing anything. It sees that count shift left 1 is going to be 0, 0, 0, 0. And crucially, it sees that the current value of count 3 is a 1. It holds on to those two pieces of information. Then it does the assignment. Count becomes 0, 0, 0, 0, but at the exact same instant, count 0 becomes 1. And the final result? 0, 1, 0, 0. Perfect. The 1 rotated exactly like we wanted. Okay, that case study makes the difference painfully clear, doesn't it? So how do we make sure we never fall into that trap? Well, lucky for us, it really just comes down to 2 simple golden rules. Follow these and you'll be in great shape. Rule number 1. When you are writing code for sequential clocked logic, we're talking about anything inside an always-at-posed clock block that's meant to become a flip-flop, you always use non-blocking assignments, the less than operator. Why? Because that's how real hardware works. All the flip-flops in your design grab their new data at the exact same instant on the clock edge, and this is the only way to model that behavior correctly. And rule number 2 is just the flip side. When you're describing pure combinational logic, the stuff with no memory, use blocking assignments, the equals operator. The one thing after another nature of blocking assignments is perfect for describing how signals flow through a series of logic dates and creating things like priority logic and an if-else statement. So here's the thing to always keep in your head. Verilog isn't just another programming language. It's a hardware description language. Your code is literally a blueprint for a physical circuit. So the next time you go to type an equal sign, just take a half second and ask yourself, what am I actually trying to build here? Am I describing a flow of logic that happens right now? Or am I describing the synchronized dance of registers on a clock tick? The answer to that question tells you exactly which one of these to use.